think everyone's coming in and the
Mhm.
recording's in progress. Okay. I think I'm just going to start with the introduction, and while people are coming in,
Mhm.
I can just talk. So, hi everyone. My name is Celia Chari. I'm a material scientist and a conservation scientist based in Washington, D.C. And I'm very excited to be here today as the host for a new webinar series of the American Ceramic Society. It's called Material Science Pioneers in Art and Archaeology. And this idea has been in my brain for a few months now. I really wanted to create a platform like this for young researchers and rising stars in the field to talk about how exactly material science can be applied to answer art historical and archaeological questions. And because it's ACerS, we're interested in ancient processing techniques of ceramics, but also glass and inorganic pigments in this webinar series. And we will have one speaker a month for the rest of the year. So this is the season for 2026. For some of you in the audience who might not be familiar with ACerS, it's a professional society for ceramic and glass researchers. Some of our members are in industry, some are in universities, and other research institutes like museums or national labs. And ACerS as a whole is made up of 11 divisions. One of them is the Art, Archaeology, and Conservation Science division, of which I'm the Young Professional Network representative and also the host of this webinar series. I also have a co-host. Her name is Julia Esikoff. She's a graduate student at the Colorado School of Mines, and she's going to be hosting those webinars that are presented by graduate student speakers. So I'm sure you'll see her throughout the year. Um, I will also say that AACS is quite busy this year. In addition to the webinar, we're also hosting a symposium at MS&T in October of this year, and it's called Scientific Methods in Art, Archaeology, and Art Conservation Science. We are currently accepting abstracts. They will be due May 1st, but I just want to mention that we would like to highly encourage students to submit abstracts for talks and posters, especially if your research is at this intersection of art and material science. And one last thing, I'm going to put up a link in the chat. If you're a graduate student, so pursuing your master's or your PhD, and you are not currently a member of ACerS, but you're interested in the society and also in AACS, the AACS division can cover membership through the Global Graduate Research Network. So if you are interested, I would ask you to fill out the form that I'm going to put in the chat and send it to Vicki Evans. I will also put her email in the chat. There is a section in that PDF that asks for payment. Do not fill that out at all. Just put in all the other information, send that over to Vicki, and the AACS division can cover the membership for a year. Um, and yeah, I think those are all the housekeeping notes, and we're ready to present Clément. Dr. Clément Holé holds a PhD in material science from Toulouse University in France, where he worked on the growth of epsilon ferrite in Chinese brown glaze ceramics. Dr. Holé is a beamline scientist at the European Synchrotron radiation facility, where he previously carried out his postdoc, working in beamline ID21 that uses micro and nano X-ray microscopy and spectroscopy. Today, he will share with us his talk on exploring the material science aspects of tea drinking and the Song Dynasty, and I'm very intrigued to hear this. So let's please welcome Dr. Holé.
Thank you very much for this introduction. I want to thank very warmly Dr. Celia Chari and Vicki Evans for the organization of this whole talk and this invitation. I'm very grateful. And I will take this invitation as an opportunity to summarize the work I've done on Song Dynasty teaware. So I worked on these materials for now 6 years, and I think it would be a great opportunity to summarize this through this webinar. So the outline of my talk will be the following. First, I will take advantage of the time I have to introduce the tea drinking practices from the earliest practices in China to the Song Dynasty. And then we'll go around this very specific epsilon iron oxide and why it's so specific to black to brown Chinese glazes. And then we will go more into the material aspects of things with studying the growth mechanism and how this very specific phase is stabilized in brown glazes. And finally, we will use this knowledge about the growth mechanism to document the manufacturing techniques that were used by the Song potters. So if we try to date back the discovery of tea in China, you will most certainly find the legend about the divine farmer Sheneng. And so there are several versions of this myth, but basically it was this ancient god that wanted to try the different plants to see if they were harmful to humans or not. And one day he ate something like 70 plants that made him very, very ill. And to recover, he wanted to drink some hot water and try to digest this. So he prepared this, his fire and his water pot under a big old tree. And by chance, some wind just detached a few leaves from this ancient tree, and the leaves fell into the boiling water, and they infused there. And when he tried it, he felt very well. He felt energized and much better. And this is how this deity discovered tea. Now, if we go to more concrete evidences of tea cultivation and consumption, we have several documents that date back from the Han Dynasty. So the first cultivation is documented during the Guanlu era of Emperor Xuan of Han. And we have more or less at the same period, one of the earliest known references to boiling tea in a document written by Wang Bao. And a bit later, we have some kind of tea recipe and tips in the Guanyue dictionary that was written by Zhang Yi. And in this dictionary, we find this quote: "People who wish to brew the tea first roast the cake made with the tea leaves until it's a reddish colors, pound it into a powder, put it in a ceramic container, and cover it with boiling water. They stew scallion, spring onion, ginger, and orange peel with it." So at this time, it seems that tea was more consumed as a brew with many different spices and vegetables. Now, probably the most important document relating tea consumption is ancient China, comes during the Tang Dynasty, and is the first known monography fully dedicated to tea, is Yulu's Chajing. So this text is divided in several chapters, and I selected two quotes that I found very interesting. And the first one comes from the chapter 4 about the utensils used to drink tea. And you can see that Lu Yu had very strong opinions on what to use or not to use to drink tea. So he states, "There are many different kinds of tea bowls, each with a different provenance and style of manufacture, representing the many different kilns. In the order of superiority, they are Yuechu, Tingchu, Wuchu, Yuechu, Sochu, and Hongchu. Some think that Xingchu wares are better than Yueju ware, but I do not agree. Yue wares are celadon, which is good for tea because it will bring out the true color of tea, whitish red for a light red tea, for example. Such a red tea would look rusty in a white Xing ware, and the yellowish show ware cast a purple hue on the tea. The brownish Hong ware make tea look black. These last three bowls are not as good for tea." So as you can see, during the Tang Dynasty, the main trend was to go towards lighter glazes with very light colors, whites, light greens, light blue with the typical celadon colors, and the yellowish showware. And the brownware were not so much appreciated. However, when Lu Yu discussed the tea brewing, he actually takes a lot of time describing some foam that can form at the surface of the tea. And so I will read once again, so this time from chapter 5, tea brewing, this part. One should let the froth settle and spread evenly in the bowls. A thin froth is called mo, while a thicker froth is named bo. The former is like a bright green algae floating near the river's edge, or a chrysanthemum blossoms falling into a bronze vessel used to brew medicine. The thicker kind of froth is created by overboiling the tea. The longer it boils, the heavier the essence becomes, and the froth accumulates. This is not unlike the layers of snow that grow on the ground over the course of a winter. The light and frail froth is termed hua, not unlike date flowers drifting across the surface of a pond, or young duckweed just budding in nascent waters, or even a wispy cloud brush across a clear blue sky. So as you can see, this has many beautiful images just to describe the tea foam. And why I wanted to bring your attention on this foam is that it's considered to be very important. So according to the record of Tonjun, which is an ancient treatise about medicinal plants, which unfortunately has been lost, but was well documented and quoted by many, many authors, the white foam of tea is both delicious and medicinal. And according to this record, there is no such thing as drinking too much of this very specific foam. And this foam will become actually the way of really enjoying tea during the Song Dynasty. First, and it's during this dynasty that the whipping of the tea will be used more and more. So they will use this type of whisks. And they will whip the tea during their preparation inside the bowls to try and create the longer lasting foam possible. And at the beginning, this was done by tea maker as a guarantee of the quality of the tea, because this foam is so delicious and medicinal. But later during this, the Song Dynasty, it became actually a literacy activity through what they called tea competitions, or docha, where noble people will just gather together to drink tea, and everyone will whip their own tea to create this foam and compare their foam to try and have the better one, the one that lasts the longest, that sticks toward the sides of the bowl. And sometimes they would even draw with a bamboo stick some landscapes on them. And when you are trying to optimize the white foam to enjoy your tea to the best way possible, having light colored glazes is not necessarily the best highlights, the best way to highlight the whiteness and the brightness of the foam. And that's why during the Song Dynasty, the aesthetic preference completely shifted towards black and brown, very dark glazes. And here we have an example from the treatise on tea by the Emperor Song Huisong, so a person of major importance in the Song Dynasty. And he wrote in 1107, "The most exquisite tea bowls are dark bluish black with delicate white highlights called rabbit's fur or marbled jade. Such bowls contrast with and heighten the whiteness of the tea froth. It is important for a tea bowl to be slightly higher and wider at the bottom than a rice bowl. The extra space allows for more breadth to whisk the tea, ensuring a fluffy, cloud-like foam to form over the tea." And this is one of the most important treatises discussing this black ceramics, but there are actually many, many more. And this typical rabbit's fur decoration that he's referring to are these brown streaks that actually run down the black background of the bowl. So you can see here an example from the collection of Musée Georges Laby. You can see that it has a thick black glaze that is applied on the on the top of the bowl, but the foot of the bowl remain unglazed. And you can see here actually some drop of glaze actually flowing through, giving a more rustic and refined appearance. And from the lips toward the inside, you have this very typical brown streaks. And here you have an example of a sample that I took under the binocular, and you can really see these brown patches actually flowing toward the bottom of the bowl and mixing with the black glaze underneath. We can also find many representation of the time of this type of bowls. So here, once again, work from Emperor Huizong. It's a painting representing a tea drinking scene from a literary gathering. And you can see here someone handling many black and brown bowls that are very, very similar to the one presented here. Now, so let's focus a bit more on this very specific black to brown ceramics. So this is a very, very wide and heterogeneous family of Chinese ceramics, and they were manufactured in mainly 3 wide areas according to the different inventory found in museum and specialized literature. So the first area, which is the most well-known one, is northern Fujian, close to the Qian kilns. So it's this red area, and that produced this very highly praised ceramics. And some display other types of pattern. You have some with silvery spots on a black background that are called, for instance, the oil spots, and are among the most precious one, and others with blue reflections that are also very, very rare and popular. Then you have a second area in South China around the Jizhou kilns, where they produced very different glazes. So they were black, and they were decorated with some more yellowish patterns, either with paper cut decoration, or here you can see the leaf type of glaze where you have the imprint of a relief that was deposited on top of the glaze. And finally, you have a very, very wide area in North China covering many different provinces that manufactured many types of different ceramics. So you have the typical homogeneous brown one that are sometimes referred to as sauce or persimmon glazes. And you have some black with brown spots that can be seen in a way as imitation of Herfur's tea bowl, because when the emperor and the aristocracy states that your bowls are the best, of course, many different kilns will try to produce them and to try and sell this type of ceramics. And this, the manufacturing techniques between the 2 areas were actually very, very different. So in the northern area, the kiln type was the manteau kilns, which were relatively small dome-shaped kilns, while in the south, it would be dragon kilns that can actually, so they were built along slopy hills, and they can extend down to more than 100 meters in length. So it was really mass production inside. Several thousands of ceramic could be fired at once in these giant kilns. The raw materials were locally sourced. So you can see that in North China, it's mostly iron-rich loess, which has like this yellowish color, while in South China is what they call the glaze stones, which are much more red. And even the fuel was different. In the north, during the Song Dynasty, you have the wood to charcoal transition. And many authors suggest that they use charcoal in this type of kilns, while in the south, they continued using wood. Now, what's interesting is to illustrate also the change of perspective about brown and black glazes. I quoted these three authors that I think show really this change from not very interesting wares. So the first quote from Powell, where he states that the northern brown glazes were primarily intended for storage rather than from the refined tables, so they were not very considered. And then you can see in Crick's quotes that there is still some differences to be made between this type of brown ceramics. And she states that black glazed stoneware were indeed initially considered for everyday use, but a few kilns manufactured refined objects that were treated with exceptional favor. And in these few kilns, we can notably think about the Jan kilns and the tin kilns that produced very high quality brown glazes. And finally, we have here a quote from who says that the teaware from Song Jan kilns were considered to be of superior quality and constituted as such the aesthetic consensus of cultural life. So it's a very strong statement that I think encompasses well how these ceramic were actually appreciated. It was really an object of admiration for the exceptional ware. Now, if we look at how people analyzed and tackled these ceramics, so they are much less popular or famous than the Celadon or blue and white, but we still have a few early analytical observations, notably in this paper from Carl Beck, and he noted that the glaze has a very particular microstructure, what he called nut brown glaze just on top, a very thin layer that is sitting on a black glass-like slip. And we can find indeed this very specific stratigraphy in this example, which is a sample that the section of a sample from Yaozhou kilns. So it's not exactly the same sites, but they are both in North China. And you can see this very thin brown layer that is running a bit down. And now you have after the black, darker glaze sitting on top of a very high quality porcelain-like body. So one of the main analytical investigation that was made on these type of glazes in the early 2010s was the study from Li et al., where they analyzed several samples from Tian kilns, and they using SEM and X-ray diffraction, and they found that the microstructure of the brown areas was very typical, with dendritic iron oxides that they identified as a mixture of hematite and maghemite. However, later looks at this type of materials showed a strong inconsistency. And here you can have the typical Raman spectrum that was recorded on this dendritic brown crystals. And in red, you have the hematite spectrum, and in blue, the maghemite spectrum. And you can see that they do not correspond at all. So it might be actually something else. And as you expect with the outline I gave, this something else was epsilon iron oxide. So this was first identified by Catherine Dejoie et al. On the Jan glazes using micro synchrotron-based diffraction. And it was also found just a few years before in some Japanese traditional stonewares. So what's very interesting with iron epsilon oxide is that it's a very uncommon ferrite with very promising properties. So it's considered to be an intermediate between maghemite and hematite. And it has in particular a high coercive field, a high Curie temperature, and it's a ferrimagnetic phase. However, one of the problems of this phase, especially for people who want to synthesize this and to use these very interesting properties, is that it's a phase that is confined in the nano scale, as can be seen here by this phase diagram by Lien Su. And since it can very easily transform into hematite, challenging the synthesis of iron epsilon oxide can be very challenging. But here we get another inconsistency. In some of the ancient glazes, we have dendrites that are enormous compared to these nanosites. We are at more than 10 micron dendrites, but they still have this very characteristic Raman spectrum that was associated with iron epsilon oxide. So why so? And what's also very interesting is that this phase is actually super common in brown glazes. So here I've taken a few examples of shards on which iron epsilon oxide was detected. So you can see that we have many different colors and hues, many different types. We have brown and black decor on white porcelain. We have pure dark brown, light brown glazes. We have black glazed decorated with brown streaks, and we have this very typical hair sphere types of glazes. And if we look at the literature, you can see that epsilon was found actually everywhere, in every site that actually produced brown glazes. And here I limited myself to the papers that were investigating kilns active during the Song Dynasty. But I have to note that there are a few Tang productions, so earlier production that still have a few iron epsilon crystals, and that this ceramics were also copied during later dynasties, like in the Qing dynasty, and we find also this epsilon. So for being so hard to synthesize, it's actually very, very ubiquitous. So one of the main questions of my PhD was actually how to explain the ubiquity of this iron epsilon oxide in ancient glazes in spite of the poor stability of this phase. So to document this, in collaboration with Shanxi University of Science and Technology and the Yaoju Kiln Ligia Porcelain Workshop, so they synthesized a series of brown glazes using the traditional firing cycle that they use, and they were sent to CEMES, where I studied to be analyzed with different microanalytical tools. So the first tool I used to characterize this series was X-ray diffraction. And from what I could see is that epsilon actually appears only on sample 7 and 8, which corresponds to only the two samples that were extracted from the kiln during the cooling step. And in the previous heating step, we have no trace at all of iron epsilon oxide. Investigating the literature about iron-rich glass annealing, I could identify a potential mechanism that would explain the growth of epsilon. And this mechanism is based on the interaction of oxygen that is introduced in the kiln during the cooling with reduced iron in the glaze. And this crystallization of iron epsilon would actually leave the glaze with some, let's say, missing divalent ion, so it will be a bit less stable. And to stabilize itself, the glaze was actually pump from deeper inside some divalent species, and these divalent species would actually fill these gaps, but then the inner glaze will be destabilized, And to restabilize itself, it reorganizes by crystallizing tiny spinel clusters. And this would perfectly explain why we have this iron epsilon oxide layer only at the surface, which has like this characteristic brown. And below, we don't find any iron epsilon oxide, and we have this very typical black layer that can be associated to magnetite, though it's noteworthy that magnetite is very rarely found in this area. This black glass is very, very amorphous looking. To go a bit further about this growth mechanism, I focused particularly on sample 7 because it was extracted from the kiln at a quite high temperature, and it displays very interesting microstructure on the surface. So you can see these tiny white dots here are identified as iron epsilon oxide. They have this Raman spectrum very characteristic. Then we have the very big dendrites that we can find in archaeological samples. And they also have these intermediate structures with both the dots from which the big dendrites are growing, showing that indeed we could have some iron concentration with the very, very small crystal at the surface. And from this spot, some crystallites would have better orientation and better growth chains, and they would actually completely grow to fully fledged dendrites. So I analyzed these different structures using TEM-EDS, so scanning transmission electron microscopy. And here you can see the 3 lamellae that I prepared. And the EDS showed a very interesting feature. So of course, we have a lot of iron everywhere because it's iron oxide. But you can see that on the very undeveloped dendrites, we have basically the same amount of aluminum inside these, let's call them bubbles, and the surrounding glaze. But the bigger the dendrites and the crystallites grow, the more aluminum we can see. And we could actually quantify this and see that indeed we have a sharp increase of the aluminum to iron ratio between the, let's say, nuclei of dendrites and the fully fledged dendrites. And what's very interesting is that the mixed aluminum and iron oxide with the same structure of iron epsilon oxide exists. So it means that the iron epsilon oxide inside brown glazes is not really iron epsilon oxide, but it's in fact a solid solution or a heavily aluminum substituted phase between this mixed oxide and pure iron epsilon oxide. And knowing this, we suppose that aluminum is actually helping this structure to grow to such enormous phases compared to the nano size that is usually confined with the nanoparticles. So we can, of course, adapt the growth mechanism, including aluminum substitution, because Chinese glazes are aluminum rich. So the aluminum can actually come directly from the glaze and participate in this growth fairly easily. And what's very important, of course, is to compare these results with ancient ceramics. And we found out in samples from Yaozhou that indeed we have in big and in small dendrites a lot of aluminum in more or less the same rates that we found in the mock-up samples. And we can even note that the bigger dendrites have slightly more aluminum than the smaller dendrites, which is consistent, which was we observed once again in the mock-up. And some colleague from the Palace Museum analyzed in parallel some Jian ware, and they found out on their side that these iron epsilon crystals also contained a high proportion of aluminum inside, showing that aluminum is indeed helping the phase to be stabilized. So now I was pretty happy at the end of my PhD. I had a growth mechanism that seemed very plausible, and we had a reason why the iron epsilon oxide was present in the glaze, a logical reason to see such well-developed dendrites. But one unanswered question was, how can we use the growth mechanism that actually I proposed to document manufacturing techniques? And this is the opportunity I had at ID21 during my postdoctoral fellowship. So here is a summary of the firing process of brown glazes. First, we have raw material, so many different types of crystalline phases that are applied on the body. They are heated, so most of them melt, some of them stay, new phases can grow. And when we cool, we will reintroduce oxygen in the kiln, and this will spark at the surface the growth of iron epsilon oxide, and below a layer of spinel. And the bigger the iron epsilon oxide will grow, the deeper the spinel should go, because we need to pump from deeper inside the glaze new divalent ion to continue this mechanism. And actually, these gradients might hide an interesting key of for documenting the manufacturing techniques and the firing processes, being in a way a fingerprint of the techniques that were used to fire, the condition in which the ceramics were fired. So to answer this question, I had a corpus of 18 archaeological samples coming from 4 different archaeological sites, Yinggu and Huangpu, both in the Shanxi province, and associated to the Yaozhou kiln complex, which was a very big kiln complex that produced a tremendous amount of ceramics. It's mostly famous for the olive green celadon glazes, which are actually called Yaozhou ware. But it produced also a very high amount of high quality black and brown ware. And then 2 different sites in Henan, Gangquan and Chengguan, both part of the Sinan complex, which is a much smaller kiln. To go alongside these archaeological samples, I collaborated with Camille Müller from Université Gustav Eiffel, who synthesized 3 reference glazes, one in fully oxidizing condition, one in fully reducing condition, and one in under air, to have an idea of the range of oxidation that the glaze can have. I also had access to pure iron epsilon oxide that was synthesized by Rachel Nicol from ESRF, and I used the commercial reference of magnetoids. To characterize these samples, I used mostly 2 techniques: X-ray diffraction for the structural characterization, knowing where is the epsilon, where is the spinel layer, etc. And for chemical characterization, I used different spectroscopy techniques, namely micro X-ray fluorescence and micro X-ray absorption near-edge spectroscopy. So for those 2 methods, I used exactly the same samples that I prepare as such. So from the archaeological shared, a sample was sampled. A fragment was sampled by my colleagues from Shanxi University of Science and Technology. And then I cut thin slices of this fragment and polished them down until I could get thin sections of about 100 micron thick that I used to do analysis in transmission mode, both for the diffraction and the spectroscopy. So let's start with the structural characterization. So this structural characterization was implemented at the ID13 beamline of the ESRF. And I also characterized the reference using high-resolution X-ray diffraction at the ID22 beamlines. And both these characterizations were implemented during shared historical material bag beam times. So just a few words about the historical material bag, which means block allocation group. So the idea is to share beam time between different teams that are all looking and analyzing heritage materials and that would require using the same setup. One of the most important parts also for us when we organize the bag is to open these techniques to new users as much as possible and to train them to use and master synchrotron-based techniques so that they are not afraid then on themselves to ask for proposal and process this type of data. And we are also developing databases and fair data, notably through the European Share project. So currently we have many partners. We already trained more than 50 new users, and we reached the, let's say, the remarkable number of more than 2,000 samples measured. So it has been, for the moment, quite successful. So here you have the name of the different coordinators of this initiative and the main parameters of the two beamline that we offer. If you want any more precision, do not hesitate to visit our website by scanning the QR code right here. So here you have a typical example of a map that was acquired at ID13. So this map is 800 microns times 800 microns with a step size of 2 micron. And I did some face identification on this map, and I was very happy to see the very characteristic stratigraphy with on top a surface here that you see in red, which when we extract the pattern contain only iron epsilon oxide. Then in green below, I have this layer that contains a little bit of epsilon, but also one spinel structure, maybe magnetite, maybe magnesiopherite, for sure it's a spinel structure. And I was very, very excited to see this layer being so homogeneous because when I proposed the mechanism, the spinel layer was likely here, but I could not actually see it. We measured a few spinel crystals, but we did not locate it as a full layer as we could with microdiffraction. So it shows that the mechanism is likely very correct. And at least it's a strong evidence of this diffusion mechanism and stabilization by spinel. So this was very exciting to me. Then we have a layer that is here in black that basically contains not so many crystals. So you can see a few colorated pixels. These are mostly due to border effects with quartz crystals or bubbles. And when you extract the pattern, you can see some peaks corresponding to quartz and cristobalite, but as you can see, they are very, very, very small. And then you see the body, which is mostly composed of mullite. Now, looking at one map is interesting, but what we want to do is compare the different stratigraphies between the sample. And I was very happy to find that we had two very different stratigraphies when we compared all samples from Shanxi and all samples from Henan. So for Shanxi, we always had this epsilon layer, then a relatively thin spinel layer, and then an amorphous layer with no specific crystalline phases found. And then below, sometimes we have a layer that contains a lot of anortites and other phases and the body. For Henan province and both sites from Henan province, the stratigraphy is quite different. So we still have at the surface this epsilon layer, but as you can see, it looks a little bit thicker. Here, all the scales are exactly the same. But what's the most, let's say, eye-catching is the presence of this very, very thick spinel layer that extends almost down to the body, or really down to the body. So this is a major difference. And knowing that the spinel is linked with the depth to which the diffusion mechanic extends shows that actually the firing conditions were quite different, because for the diffusion mechanism to happen, you need the ions being able to move, so you need quite high temperature. And on one side, you have the spinel layer, so this diffusion only occurred at the surface. And on the other side, it went down to the body, while the glaze thickness are more or less comparable. So the firing were definitely different between Shanxi and Henan analyzed sites, but also interestingly, Yaozhou and Yingguo sites have similar stratigraphy, and Gongquan and Chengguan kilns have similar stratigraphy, so similar manufacturing processes, let's say. So now, to go a bit further, we did some chemical characterization, and this was done in the scope of the internship of Louis Lebert that I supervised. And he did an amazing job. He was very efficient at processing the data. It's him that you can see here. And we implemented this at the ID21 beamline of the ESRF, which is the beamline where I work. So this is a micro and nanoscopy beamline, and we have a beam incident energy from 2.1 to 10 kV, which allow us to assess the chemistry of many different elements. And if we consider the K edges from the phosphorus to the zinc K edges, we work under vacuum to reach this low or tender X-ray energy. And our sample environment can be either in ambient temperature and static cryogenic conditions. And we have two microscopes. The first one is the SXM2 that has two modes, the unfocused mode with quite a wide beam, which is defined by slits, and a focused mode focused by nickel-coated cables, and that gives a submicron beam. And then we have the brand new nanoscope that was open to user in 2024, in which we have only focused mode accessible with either nickel or platinum coated optics, and we can reach beam sizes down to 100 nanometers times 100 nanometers. So just note that all the experiments that and the data I will show you next comes from the focus mode of the SXM2, so with this type of micron beam or submicron beam. So in case you are not familiar with X-ray absorption spectroscopy, a very basic slide to explain quickly what does an absorption spectrum looks like and some parameters that we can see. So the idea is to scan the incident energy around the electron binding energy of one element. So this is very interesting because it makes it an element-specific technique. We'll excite only one element and look how its excitation varies depending on its chemistry. And this allows to document the average local chemical environment of an element of interest. And in this case, I looked at iron. What's interesting is that it's both sensitive to amorphous and crystalline phases, which is particularly relevant when you want to look at glazes. And here you have the example of the references that I measured and used for this study. And you can see that basically the more oxidized iron is in average, the edge, which is this step here, actually shifts toward the higher energies. And by using the shift, you can actually have a qualitative idea of the average oxidation state of iron inside your sample. So now we come back to our sample example. So here you have the XRD map on which I overlaid two fluorescence maps, which are the difference in energy between energy 2, which is maximal when iron is very oxidized, and energy 1, which is maximized when iron is reduced. And I selected from this map several points here that you can see in black. and the spectra associated are presented here. And you can clearly see that from the surface toward the depth, we have a clear shift of the edge from the high energy toward the lower energy, which hints at a reduction of iron. So iron is very oxidized at the surface and less oxidized in depth, more reduced in depth. And if we plot this point, the middle here, we can reach this type of profile. So here I drew several line scan profiles over my surface, and I could draw this oxidation gradient for this specific sample. Now, what's interesting is to compare the different samples. So here you can see all the samples mixed together. And to make things a little bit clearer, I divided the provinces into different graphs. And what I was very excited to see is that the two different graphs show very different trends. So when we look at Shanxi province, we have every time a rather sharp oxidation gradient, and then we reach a plateau which has the same average oxidation states to the highly reduced glazed. So that was synthesized in laboratory conditions with 5% hydrogen and 95% nitrogen. And in Henan province, the data it's much more spread. We have sometimes very sharp gradients, sometimes much smoother gradients with plateaus in the middle, etc. So what we can also see, and by remembering the diffraction data, is that in the case of the Shanxi province, there was no spinel in the bulk of the glaze which corresponds to here. So it means that the bulk of the glaze was not affected by the growth of iron epsilon oxide, and it captured the information about the heating step, the atmospheric condition inside the kiln chamber when the glaze began to melt. So then once melted, there is no oxygen exchange possible with the atmosphere or gaseous exchange apart from rising bubbles. So here it suggests that the heating steps of Shanxi firing was very reducing. For Henan, unfortunately, because the spinel layer goes all the way through the body, it was affected by the growth of iron epsilon oxide. So we cannot infer much about the heating step, but seeing this widespread type of gradients, we can infer that actually the cooling conditions were much less controlled, much less reproducible, which would be in agreement with archaeological observation, because these two sites are much smaller and were producing much less brown glazes than especially Yaochu, which was one of the major kilns in terms of quantity of ware produced. So to conclude a little bit this whole presentation, black to brown glazes were developed. So it's really a material that was developed considering the aesthetic preferences of Song tea drinkers. They wanted dark and beautiful materials to have a nice contrast with the white foam that they enjoyed so much. And this material that was developed actually has this characteristic color, and due to superficial layer of micrometric dendrites of aluminum of iron epsilon oxide on top of an iron-rich glaze. And iron epsilon oxide is considered to be not very stable and is very uncommon. And it's ubiquitous in brown glazes, no matter where they were synthesized, in which conditions, and across many centuries. So they are actually stabilized by massive amounts of aluminum substitution. We are almost to a solid solution between the AlFeO3 and the real epsilon oxide. And this oxide grows at the surface of the glaze through a diffusion mechanism that lead to this very specific stratigraphy of an epsilon layer, then a spinel layer, and then sometimes the unaffected glaze. And this stratigraphy can be linked to the firing parameters and can be used to document the firing conditions. So it was applied to compare sites from Shanxi and Henan provinces, and we saw that the firing conditions were different. In Shanxi, the heating step was carried out in reducing conditions, and the cooling step was quite reproducible because we have always this very well-controlled gradient. In Henan, the heating steps condition cannot be inferred with certainty because we have the extent of the spinel going all the way through the body, so the diffusion actually modified the average oxidation gradients in the whole glaze. And the cooling step was less controlled because we can see a wide variety of oxidation gradients of iron inside the glazes. So I want to thank you very much for your attention. I hope that everything was cleared. I also want to thank very warmly many colleagues, in particular my colleagues from ID21 and Marine Cote, which was key in continuing this project and making it possible to implement. I want to thank also very warmly Philippe Sio from CEMES and Sophie Duhem from Framespa, who were my PhD supervisor, and with whom this adventure would not have started. And of course, the Chinese partner from Shanxi University of Science and Technology, notably Tian Wang and Zhen Zhao, who were wonderful partners, very reactive. It was a pleasure, and it is still a pleasure working with them. And finally, I want also to thank Louis for his amazing work as an intern. If you have if you want to dive a bit deeper on this topic, we have quite a lot of publication related to the study. So do not hesitate to have a look and contact me if you want to further the discussion. Thank you very much.
Thank you so much, Clément. That was an amazing talk. For the audience, if you have any questions, please use the Q&A box to fill them in instead of the chat. To start us off, I have a couple of questions that I'd love to ask. I really want to go back to slide number 42, where you have that combination of XRD and Zanes.
Wait.
42.
Here.
Yes. Okay, so my question has to do with that interface between the epsilon layer and the spinel, because in XRD, it is so well defined. It nearly looks like there are two layers applied. But then with Zanes, you can see that there is more of a diffusion, like more of a gradient from one oxidation state to the other. So what are the exact mechanisms that are defining this epsilon phase versus spinel, and how does that relate to the oxidation state?
Okay, so thank you very much for your question. So I will quickly go to one of my supporting information slides, which is an example of one sample. And here you can see the profiles, integrated intensity in red of epsilon and in green of spinel. So you can see that the clear difference is actually more of an artifact. We have some spinel in the epsilon, and we have some epsilon in the spinel. And one other important aspect is that, unfortunately and fortunately for us, Xanes is sensitive to all iron in an equal extent, which means that on the surface, I don't see epsilon. I see epsilon plus the remaining iron that is trapped into the glass.
That makes sense.
And though epsilon is clearly defined as only iron 3 plus, and spinel is likely a mix of iron 3 and iron 2, in the glass, I have this real gradient of iron 2 and iron 3, and the deeper I go, the more iron 2 I get. And this explains why I have such smooth curve, because actually the crystals are not the main phase. I have a lot of glass, and this glass is contributing significantly to the Xanes signal.
Yeah, that makes complete sense. Thank you for clarifying that. Okay, we do have another question, which is actually funny because this was going to be my second question. You mentioned some of the interesting magnetic properties of epsilon iron oxide. Does
Mhm.
the aluminum stabilized epsilon iron oxide retain these properties? And would it be possible to stabilize the epsilon phase with other trivalent dopants?
Thank you very much for your question. So this is actually what I'm currently investigating with Rachel Nickel from ID32. So she is a specialist of iron epsilon oxide, and during her PhD, she worked with different metal-doped iron epsilon, so with, let's say, transition metal. From the literature, it's possible to stabilize the gallium iron, let's say, epsilon oxide. So gallium can stabilize big crystals, but the magnetic properties are generally worsened by this substitution because they can cut some of the exchange interaction. So currently, we are still trying to investigate these properties. So what I saw from some micromospower experiments that I presented during SR2A 2025, so these are quite new results, I could see that in the areas where I have iron epsilon oxide, the Mospower the Mospower values of hyperfine interaction are very similar in, let's say, the ancient epsilon. So you can see here. And when we compare them with the pure epsilon, they correspond well with the different sextets that we expect. However, it's interesting to note that in pure epsilon, we should expect another sextet with a much smaller hyperfine constant, which would correspond to iron in tetrahedric position, which we do not find at all in ancient epsilon. So it suggests that actually the aluminum is going on this site, is preferentially substituting this site. And this can play a role in the ferrimagnetic properties because these different sites are the ones that are giving this ferrimagnetic properties. So if one disappears, what will happen? So it's still under investigation. It's a hot topic. And I hope that I will be able to answer to your question with more detail next year with what we are going to do. But thank
Yeah.
you.
Yeah, definitely. There is one quick question that I think you can answer. Thanks for a fascinating talk. Presumably, the Song
Thank you.
Dynasty wasn't quite advanced enough to manufacture cylinders of forming gas with 5% hydrogen, smiley
Mhm.
face. So how were reducing conditions obtained in the kilns?
So these were typically obtained by burning either resin-heavy essences of wood or wet wood. And when you burn this type of woods, you would create so I don't know how to say in English. In French, we have this expression gaz à l'eau, which is basically gas with water, which is a chemical reaction that transforms H2O and CO2 in H2 and no, H2O and CO in H2 and CO2. So you will create actually, you can create H2 and CO with incomplete combustion, which are very, very strong reducing agents.
Okay, there's other questions, but it's mostly comments about where in Japan. I can send them to you later. I think we're running out of time. So
So
I will.
maybe if I just can make a very quick comment about Japan. So in Japan, indeed, these ceramics are very, very precious and they are considered as national treasure. And they are referred to as Tenmoku, which is the Japanese transcription of the Tianmu mountain here. And it's the Japanese monk who first imported these tea bowls that actually named them the name of the mountain, but they are indeed major cultural artifacts. And just as an anecdote, you can even find some bowl plushies to show how like important they can be.
Wow.
It's like this type of goodies that sounds very strange.
And I guess the comment here was it would be interesting to see if some of the phases that you're finding are in those wares, and I
Mm,
imagine there are too then. Okay, that's
so
really cool.
definitely when it's Chinese imported ware, on the later ware that was manufactured in Japan, I don't know. But indeed, it would be very interesting to
Mm,
investigate this.
okay. Okay. Well, thank you so much, Clément. I think, yeah, we'll call it a day. Let's thank Clément one last time. And just to quickly let you know, in a month's time, there's going to be a second talk in this webinar series, and we're going to be looking at iridescence and structural color and examples of that in feathers. So I hope to see you in next month's talk. And thank you again, Dr. Holé, for this month's talk.
Thank
Bye,
you very
everyone.
much again, Celia, for the introduction and the invitation. I was very honored to be here. Thank you.
Thank you. Thank you. Bye.
Bye.